So consider the following definition. We have, let's say, G and H are groups. And I want to say that a function phi from G to H is an isomorphism. It's a very important word. An isomorphism if, well, number one, phi is a morphism, a group morphism, so I should say morphism of groups. And number two, phi is bijective. So recall that bijective means we're both one-to-one and onto, or both injective and surjective. So one-to-one means for every, let's say, every two elements, G and G prime, in G, if phi of G does not equal, so if phi of G does not equal phi of G prime, so I should say it like this. I should say if phi of G does not equal phi of G prime, then G does not equal G prime. So that's what it means to be injective. It's what it means to be one-to-one, formally speaking, and then onto or surjective. So this is also called injective. It's called surjective. This is for every H and H, there exists a G and G such that phi of G equals H. So when you're a bijection, one thing that you should prove for yourself as an exercise, if you haven't seen this already, is given a bijection, we have an inverse map. We get an inverse map, V inverse from H to G, which is also a bijection. So somehow bijections between, so if we forget about the fact that G and H are groups and just think about them as sets, a bijection is somehow saying that these two sets are going to be the same. And these two conditions right here are just what you need to construct the inverse function. The idea behind an isomorphism, especially an isomorphism of groups, a group isomorphism, is that we have a bijection, but it's also somehow respects the structure of the group. It's a morphism of groups. And so there's this lemma, which we'll prove. So here's the lemma. The lemma is if phi is a group isomorphism, then phi inverse is also a group isomorphism. And what this will tell us is that based on these isomorphisms, because they're homomorphisms, any computation, if we have an isomorphism, any computation that we do in the group G works in the group H, and any computation that we do in the group H works in the group G, vice versa. So somehow the idea of being isomorphic is the same thing as the idea that these two groups are the same group somehow. So here's the proof. We need to show that phi inverse is a group isomorphism. Phi inverse, by the exercise, is already a bijection. It's also a bijection. So, and because of the definition, we need to show that it's bijective, which we have, and we need to show that it's a morphism of groups. So we need to show that phi inverse is a group morphism. Which is to say the same thing as phi inverse of AB is equal to phi inverse of A is phi inverse of B. That's for all A, B in H, right? Phi goes from G to H, phi inverse will go from H to G. So what we can do here is we can say, well, the idea is going to be, we want to prove this using the fact that phi is a group homomorphism. So we need to reframe this in terms of a question about something about phi. So let's first let's first consider what this side looks like. So if I apply phi to phi inverse of A, phi inverse of B, so right, this is an element of G, this is an element of G, I can multiply them together. I don't yet know that they're equal, right? This is a question mark. But I can consider this right here. And because phi is a group homomorphism, I can split it up like this. I should write phi of phi inverse of A times phi of phi inverse of B, just like this. So that's by the fact that phi is a group homomorphism. Now, because these are inverse functions of each other, this is the same as A times B. But now A times B is actually the same as, right? A times B is the same as phi of phi inverse of A times B. So what I have here is I have on this side, on the left hand side, I have phi of one side of the equation I want, and on the right hand side, I have phi of the other side of the equation, and they're equal. So the images under phi are equal. But phi is a bijection. Phi is a bijection. In particular, it's one-to-one. So if I have, phi of this one side, phi of phi inverse of A, phi inverse of B, and that equals phi of phi inverse of AB, that's going to imply that phi inverse of A, phi inverse of B equals phi inverse of AB as desired.